Now that we have all the files that we need to run our program, we will need to compile them as a single unit. To do that, we will go to Rebuild. After clicking Rebuild, notice that a lot is going on with our compiler. Later on, we will see additional files that has been created by our compiler by taking a look at the location of our project. For example, here are some of the files which were generated as a result of the compilation. As you can see here, we have the following files with the following extension. These are object files that were generated by our compiler during the compilation of the following files, especially our header file, which is the interface file, as well as our implementation file. And of course, they were compiled as a single unit, hence, we are now able to run our program through our program file. Let's take a look. So here we go. For now, let's provide it with an input. Let's say I'm going to put John. By just taking a look at the output, there's nothing interesting to see there. But anyway, let's take a look at the actual source code to know what's going on. First, let's take a look at our implementation file. In the implementation file, which was stored as a CPP file, as mentioned, this is where we place all the definition for the class members, such as constructors, as well as member functions, as we see here. Next, this program actually involves dynamic variables. Of course, as we've mentioned a while ago, dynamic variables will not go away unless delete is called, hence freeing up the memory that has been previously occupied by your variables. Even if a local pointer variable goes away at the end of a function, the dynamic variable it pointed to remains unless delete is called. A user of the string var class may not know that a dynamic array is a member of the class, so could not be expected to call delete when finished with a string var object. That's why we need a function called destructor. As opposed with constructor functions, a destructor function is a member function that is called automatically when an object of the class goes out of scope. That is, the destructor contains code to delete all dynamic variables created by the object. A class has only one destructor with no arguments. The name of the destructor is distinguished from the default constructor by the tilde symbol. Here's an example of how we declare a destructor. Let's go back to our sample program. Going back to our implementation file, we have the following constructors. As you can see here, we have three types of constructor. Although this one is also a kind of a constructor, but this is actually called a copy constructor. We will deal with that later. And of course, this is the destructor function that we are referring to in our slide. As you can see here, it somewhat looks like a default constructor, but of course, it is distinguished by this symbol. With this symbol, the C++ compiler is told that this is the destructor for our class. And as you can see here, the destructor contains the code which gets rid of all the objects and all the values that were created by the class members during its execution. And of course, it also makes use of the delete operation. The destructor in our example must call the delete operation to return the memory of any dynamic variables to the free store. As you can see here, it is still concerned with memory management, which has the primary goal of freeing up memory that has been used and returning it to the free store. Here's an example that we have seen a while ago. And of course, there are also instances that we use pointers as call by value parameters. Using pointers as call by value parameters yields results that might not be expected. We must remember that parameters are local variables. Hence, their existence is only expected to be within the function to which they belong. No change to the parameter should cause a change to the argument. But of course, in the case of pointer variables, that could be a different scenario. The value of the parameter is set to the value of the argument, which contains an address stored in a pointer variable. The argument and the parameter will hold the same address. If the parameter is used to change the value pointed to, this is the same value pointed to by the argument. To show the scenario, here's an example. In this case, we have declared a type def of type in pointer with the name p, and of course, we use it as a dynamic variable. And this time, we assigned the pointer variable p with the value 77. Next, we call the function sneaky, passing p as an argument, and in this case, we are passing p as a call by value parameter. And if we will take a look at the definition of the function sneaky, this is what happens. As you can see here, we have declared another pointer variable as its parameter. And what will happen here is that the moment that we pass p as a call by value parameter, that will be captured by this pointer variable. And in this case, we will, inside the function, we will assign a pointer variable temp with the value 99. But we must remember that since p was passed as an argument to this parameter, it means that whatever address that this parameter is pointing at will be the same address that the argument p will be pointing to as a result. To see what happens, let's try to run this program and try to see if we will have the same output as we have here. Okay, as you can see here, this is the effect of passing a pointer variable using call by value reference. As you can see here, the local variable that we have here inside our function was able to override a variable which is outside the scope of this function. It is for the reason that this pointer variable was intended to pass by value, but the problem is our parameter here is actually a pointer variable which caused our variable p to point to the same memory address that this local variable is pointing to. Therefore, using pointer variables as call by value parameters can also pose a number of problems. To visualize the scenario, this is how it would look like. To solve the problem that we encountered a while ago, we need what we call copy constructors. As we have seen, the problem with using call by value parameters with pointer variables is quite an issue, especially when we are dealing with programs that use a lot of functions. That can be solved by using copy constructors. A copy constructor is a constructor with one parameter of the same type as the class. The parameter is a call by reference parameter. The parameter is usually a constant parameter. The constructor creates a complete independent copy of its argument, thus avoiding the issue of overriding our pointer variables as what we have seen from the previous example. Talking about our copy constructor, this is how our copy constructor would look like in our actual implementation. As you can see here, the parameter is a pointer variable which is of the same type as its class. And in this case, what happens here is that it creates a separate copy of the parameter that is being passed to this constructor function, and therefore a separate independent copy is generated, therefore not affecting the original one. As shown in this code, it creates a new dynamic array which is intended to be a copy of the original argument. Thus, it protects the original from whatever changes that might happen during the program execution, especially within the function in which a pointer variable was involved. How do we call a copy constructor? A copy constructor can be called as any other constructor when declaring an object. The copy constructor is called automatically. When a class object is defined and initialized by an object of the same class, when a function returns a value of the class type, when an argument of the class type is plugged in for a call by value reference, thus making our formal parameter safe from whatever change that might happen, since we already have a copy of it. So when do we need a copy constructor? Here's a sample code which shows why we need a copy constructor. When the function showString is called, this argument, greeting, is copied into this formal parameter, the string. As a result, the value of the string parameter is set equal to whatever value is in this variable named greeting. In this case, since greeting.value and the string.value are pointers, they now point to the same dynamic array. So that might cause some conflict. When the instance of showString ends, the destructor for this object executes. In this case, the string, therefore, returning the dynamic array pointed to by the string value to the free store. Therefore, if showString and the string are pointing to the same memory address, after the destructor function of the string is called, this will leave showString pointing to the same memory address that has been deleted. So that could be a problem. This could be the result. This pointer variable now points to a memory location that has been given back to the free store, which is at this point undefined. Two problems now exist for the object greeting. First, attempting to output greeting.value is likely to produce an error. Although in some cases, it might go okay, but the point is, it might result to unpredictable output. Another one, when greeting goes out of scope, its destructor will be called. Thus, calling a destructor for the same location twice is likely to produce a system crashing error. Based on the same example, but with a copy of the constructor defined, we now have the following. As you can see here, the respective value contained by each variable points to a different location in memory. When the string goes out of scope, the destructor is called, returning the string value to the free store. But of course, this would not affect the other variable, greeting, which contains its own copy of the data, which is in this case, the dynamic array, which contains the C string hello. So when do we need to include a copy constructor? When a class definition involves pointers and dynamically allocated memory using new, it makes sense that we use and include a copy constructor.